Okay, so our next speaker is going to be Nicholas LaRacuente, and he's going to talk about multivariate trace inequalities, recovery, and p-Fidelity beyond tracial settings. So I'll give you the floor.
Hello. So I'm going to talk about a combination of trace inequalities and entropy inequalities based on recovery maps. These are mathematically connected concepts, and one common theme that they'll have is that recently there's been a lot of interest in getting these type of inequalities in the infinite dimensional setting, and not just in any infinite dimensional setting, but in sort of a variety of infinite dimensional scenarios in which some of the usual constructions of matrix theory would just not quite work out. For example, we may not have a trace in some of these algebras. So first, I'd like to thank the organizers and also the audience for being here and listening. I would also like to thank the various sources of support I've had in this project, including the University of Chicago, IBM, the University of Illinois, and the National Science Foundation. So there is an archive version that has most of the content of this talk. It will be updated soon to have everything. So if you don't see everything on the archive paper, that's because we are just getting things ready to post in their more final form. And I'd like to start off by introducing von Neumann algebras, which are one of the objects we will consider here, in a very familiar setting. So I'm going to start with finite dimensional von Neumann algebras of what we call type 1. And these are algebras in finite dimension or on finite dimensional Hilbert spaces. So for a system of several qubits, we can take a multi-qubit Hilbert space that is a tensor product of two-dimensional Hilbert spaces. We, of course, have the usual bracket notation and the inner product. We also like to consider the matrices on Hilbert spaces, or what we might think of as the bounded operators, so matrices with finite entries, finite eigenvalues. And these include things like the unitaries, the transformations, the Hermitian observables, the projectors, the densities. All of these are inside this class of bounded operators. Now, we'll often denote densities in this talk by lowercase Greek letters and more general operators by uppercase letters like x and y. In a more mathematical approach, we can think of a type 1 D von Neumann algebra as bounded operators on a d-dimensional Hilbert space. We also have von Neumann algebras that are block diagonal subalgebras. So these actually can correspond to taking a partial trace or a measurement or a partial measurement, and this will lead to an algebra that is not the full set of matrices on the Hilbert space, but is this restricted set that will have a block diagonal structure. Now, these, of course, have a trace. The trace is a sum of eigenvalues. And we can take the trace to be an element of a dual space, which we can also represent using matrices. When we do so, we'll find that the trace is proportional to an identity matrix. And of course, it also has this cyclic property that is really essential to it being a trace. Now, we can get an infinite dimensional system by taking the limit as the dimension just goes to infinity. And this will lead to what's called a type 1 infinity algebra. Now, what's interesting about the type 1 infinity is that the trace of the identity matrix is infinite. There's actually no way to normalize the identity. And in fact, you can find many full rank states that because they have infinite rank, unless there's some convergence of the eigenvalue series, they would actually be unnormalizable. And so in this case, we would say that it has a semi-finite trace. The trace is not infinite everywhere. Clearly, it's finite on elements of finite rank, but it's also not finite on bounded operators in this space necessarily. But there's other ways we could think of taking an infinite dimensional system. So we could, instead of just taking the dimension to infinity, try to tensor on infinitely many qubits, and so make an infinite qubit chain. And naively, this leads to an infinite vector space with uncountable dimension. There are some issues with this, but less naively, we can actually get von Neumann algebras of higher type that will have physical meaning. So the next few slides, I'm going to review some ideas that really come from Witten's review article in 2018, but actually go back to some work by Araki and Woods much earlier. And so the simplest case of where we could create a higher type von Neumann algebra using this infinite qubit chain is what's called the hyperfinite 2-1. And so what we would do here is we'd actually double the chain. We'd take two chains. And as we keep adding more and more qubits, we would impose a constraint that the infinite tails of these states start to look like just infinitely many copies of a maximally entangled state. So this will actually give us two von Neumann algebras, one for each of the chains. And in each of them, it will kind of look like all of these infinite degrees of freedom, all these extra degrees of freedom are ending up in complete mixture from the perspective of either side. And so we could take in the Hilbert space, a truncated inner product that sort of only counts the portion of these of two states where they actually could differ, where they're not just infinite copies of maximal entanglement. Take the closure in Hilbert space with respect to this inner product and sort of build up the von Neumann algebra on this. And this will give us a meaningful algebra. This will give us a possibly physically interpretable von Neumann algebra. It is, however, in some ways a different kind of infinity than the type 1 infinity. Now, if we took a non-maximally entangled state, instead of the maximally entangled state, we would also get a von Neumann algebra, in this case, what's called the hyperfinite type 3 lambda, where lambda is a parameter that actually depends on what state we chose. And we could even have a sort of cycling tail where it doesn't really converge to any infinitely repeated state. And this also gives us a von Neumann algebra. In this case, it's the hyperfinite type 3-1. So there are many kinds of infinite dimensional von Neumann algebras beyond the type 1. I showed the type 2-1. And what's nice about type 2-1 is that it actually has what we call a finite trace. The trace of the identity operator is 1 or can be normalized. So this in some ways has nicer properties even than the type 1 infinity. Now there's a type 2 infinity, which is essentially combining features of a type 2-1 with a type 1 infinity, and indeed you can construct them by tensoring a type 2-1 onto something infinite. Then there are the type 3s. I won't get much into type 3-0, but I showed the hyperfinite type 3 lambda construction and the type 3-1 construction very briefly. These have physical analogies. You can potentially look at a type 3 lambda as something like a thermal system. You can look at a type 3-1 actually, as described by Witten, as a very likely model of quantum field theory in space-time. And so these are actually von Neumann algebras that we want to study for physics. However, type 3 actually lacks any kind of a semi-finite trace. So there's really no useful way to put a trace on these algebras. Type 2 has a trace. Type 1, of course, has a trace as well. But type 3 is often the one that we're really interested in. And so what we want to do is take ideas like entropy, like information theory that we have in the finite dimensional setting, and see how these work in field theory, which probably means going to type 3. So the relative entropy is an object that comes up in many places in information theory, and in fact has been in some cases described as like a root entropy. You can take special forms of it to get all sorts of different kinds of entropy. And so To construct this, we'd like to construct this without relying on any finite dimensional ideas or even any tracial ideas. So this can actually arise from something called Tomita-Kosaki modular theory. We take a von Neumann algebra M with a normal faithful state omega, and then we can define what's called the relative Tomita operator. And that is actually with respect to two densities, rho and omega. And that's given by S rho omega acting on an operator applied to a purification, so a ket omega. It flips X to its adjoint and flips the state from a purification of omega to one of rho. And then in this standard construction, one would take the polar decomposition and get this J and this delta. And the delta here is what's called the relative modular operator. So this is all standard Tomita-Kosaki theory. There's nothing new here. And as is known, the relative entropy, we're probably all familiar with the trace form of the relative entropy. But you can also define it entirely in terms of the relative modular operator. In this case, it no longer relies on having a trace. This is one of the ways to do this in an arbitrary von Neumann algebra. Now, the von Neumann entropy follows as a special case of relative entropy. You can actually take it with respect to an unnormalized identity to directly get the von Neumann entropy. And there's also this subsystem entropy, which is really a shorthand for a von Neumann entropy restricted to a certain subsystem. Now, both of these will have the issue that in many of these field theories, by default, they become divergent. And so if you try to take, for example, the entropy of a subregion in a type 3.1, for instance, you will find that in general, that's going to be infinite. The relative entropy, however, is often more stable. If you take the relative entropy with respect to a vacuum state, that actually is more likely to be finite in these theories, even though in the finite dimensional setting, the relative entropy is the one that can go to infinity if states do not share support. Now, the quintessential inequality of quantum information is strong subadditivity. This was shown by Lieb and Ruskay in 1973, and this has a fairly familiar form. I will briefly recall that there's sort of a beautiful visualization of this that appears in holography. This is due to Heydrich and Takiyanagi. And this holographic version comes from a correspondence, or at least a proposed correspondence at the time, between the entropy of a boundary theory and the minimal surface areas in what's called a bulk theory. So here on the left, we have taken a line or a segment to be our boundary theory. This will have three subregions, A, B, and C. And so the first two terms in strong subadditivity are corresponding to AC and BC. So these are overlapping. The bulk theory is this area above this line where we would have these arcs representing geodesics. In this case, they're fairly simple, drawn as semicircles. And we could reinterpret these shapes as corresponding to the union and intersection. And note that the minimal surfaces for these, if you sort of reinterpret them as the union and intersection, are actually not minimal surfaces. These are no longer geodesics. And so that's one way of sort of imagining the strong subadditivity. It's comparing two overlapping subsystems to their union and intersection and showing this entropy inequality. Now, the use of entropy inequalities in high energy physics, again, motivates wanting recovery maps and similar concepts and improvements to classic entropy inequalities in type 3. So strong subadditivity is also very closely linked to what's called the data processing inequality. These are often considered equivalent. And data processing is monotonicity of relative entropy under applying a quantum channel to both input states. And so this is fairly well known as well. A quantum channel represents an open physical process, one that might include noise, interactions with an environment, so generally a non-invertible map. And data processing says that this can only reduce the relative entropy between two states. So this has a long history of further study. And one of the first developments on data processing that I'll bring attention to is by PETS. This is a condition for saturation or equality in data processing. It says that when there's no decrease in relative entropy, then this object called the PETS map actually is a perfect recovery map or perfectly inverts the channel on both of the states. And so here the PETS map is defined with respect to one of the states, and the channel, it's sort of trying to reverse the channel. It looks like an adjoint in some sense. And the saturation of data processing is equivalent to it also reversing the channel on the other state. So this was improved in a paper by Wilde, actually, where we have a rotated PETS map. This is now taking an extra parameter and optimizing over that extra parameter. And now this extends the equality condition to an inequality. So now we have that the difference in relative entropy under applying a channel is an upper bound for this logarithmic fidelity, which is really measuring how well the state rho is recovered by a recovery map that was given for omega. Then this was later extended to a universal recovery map. And this universal recovery map sort of takes this optimization, integrates over it, and can bring it inside. And what that means is that now we have this R tilde omega phi, and that really only depends on omega phi. There's now no longer any way for a rho dependence to sneak in. And so this was another sort of step in this progression. Now, the rotated recovery map was actually generalized to von Neumann algebras in 2020 by Gao and Wilde. This one was generalized to von Neumann algebras by Faulkner, Holland, Swingle, and Wang, and also by Junge and I in some of the first content of this talk. So there is another recovery map that I would like to, or recovery inequality that I would like to recall. But to get there, I'm actually going to take a bit of a detour and actually bring up why trace inequalities connect to all of this. So trace inequalities are very powerful in quantum information. They often replace functional calculus or even basic calculus ideas that would appear in classical information. So as an example, if we take two vectors with element-wise operations, the exponential of a sum is equal to the product of exponentials. And this holds largely because these are commutative objects. When we take two general Hermitian matrices that may not commute, we no longer have that equality. Instead, what we have is the Golden-Thompson inequality, which relates the traces of exponentials now as an inequality. So recently in a paper with Sutter and co-authors, we got a generalized they got a generalized Golden-Thompson inequality. And so if you recall the p-norm on a matrix, so the Schatten p-norm, this is given in terms of the trace with a p-th power of a positive version of that matrix. And for a set of Hermitian matrices, there is now this inequality in relating the logarithms of the p-norms. And you can see in here, again, this is relating an exponential of a sum to a product of exponentials. It's a more complicated form. It's also a more powerful form. Of course, it has this integration measure. It has these imaginary powers of the matrices. And what this will lead to is a recovery in terms of the measured relative entropy. So this dm is taking the supremum over all possible measurements. This is less than the relative entropy, but it's actually stronger than the logarithmic fidelity recovery I showed before. And this is really saying that the relative entropy difference under a channel is an upper bound for this measured relative entropy, or a measure of distance between the first input and its recovered version. But this leads to a question, which is that this came from a trace inequality, and what happens without a semi-finite trace? Does the trace inequality even make sense? Do we still get the measured relative entropy inequality? It turns out that all of this will still work, but even to make sense of it, we need to introduce some extra machinery. And so this will get into some more of the mathematical ideas that we've brought to this problem. So one of them is that of a Haagerup LP space. So given an algebra M, again with a normal faithful state, we can construct something called a cross product. And in this case, we're taking a cross product of M with the real numbers. And this is guaranteed to be of type at most 2 infinity, even if the original M was type 3. And so this has at least a semi-finite trace. We would then construct these Hagger Up LP spaces. And these are spaces that they're linear subspaces and they're L and bimodules. And the Hagger Up L1 space has a functional that we would refer to as the Haagerup trace. And it has densities corresponding to states in the pre-dual of the von Neumann algebra. These LP spaces also have Holder conjugations, and they have a Holder's inequality. They support polar decompositions, and they have a p-norm that behaves in the expected way with the trace. And so that ends up being a very useful idea. It's sort of like we're recovering many of the tracial ideas in this LP space, which, even though it isn't the same as the von Neumann algebra we started with, will allow us to do things related to that von Neumann algebra. There are also these Kosaki LP spaces. These were introduced by Kosaki. No surprise there. So the Kosaki LP spaces have a norm that's given by taking an object in the original algebra X and one space to certain powers. And this will guarantee that the product is actually in the LP space. Now, these very usefully support complex interpolation, which will allow us to derive estimates on these Kosaki LP norms. And the Kosaki LP norms have a correspondence with this generalized alpha Z Renyi entropy that was introduced in 2015. You can actually write this in terms of a logarithm of a Kosaki type norm. And this entropy subsumes, for example, the sandwiched and the Petz-Renyi entropies. And so this actually shows that there's a very direct correspondence between what Kosaki considered and the entropies that we are working with most commonly in quantum information theory. Now, it will turn out that Haagerup and Kosaki spaces are isomorphic. They actually coincide with each other. The Haagerup philosophy is essentially that once one builds this LP space over the von Neumann algebra, the trace and the norm will make sense and work in the way we expect. It turns out that the Haagerup L infinity space is the original algebra. The Kosaki philosophy says that if we take something that is in the original algebra and multiply it by some of these densities that correspond to states in the pre-dual and that actually are in the Haagerup L1 space, then that product will end up in the LP space. Another important aspect of these is that when the original von Neumann algebra was finite or has a finite trace, we can actually get back the p-norm. And so these are compatible with the finite setting, even though they don't require it. Now, finally, we also use this method known as the Hagger Up Reduction. Again, this came from this 2008 paper. And this is takes an algebra with a normal faithful state, constructs a cross product with now a discrete group that is a subgroup of the reals. This could still be in type 3, but what we gain from that is that now there's a norm-preserving faithful map back into the original algebra. And there's this family of subalgebras that are also connected with this cross product that can arbitrarily approximate states on the cross product. And these subalgebras are now all type 2-1 at most. And so these all have a finite trace, and these are fairly nicely behaved. So what we derive from this then, first we can actually get a generalized Araki-Lieb-Thirring inequality, which again, this was shown for matrices in the Sutter and co-authors paper. Now we can rewrite it entirely in terms of Kosaki norms and no longer rely on any finite von Neumann algebra assumptions. This could be a type 3 object. There may not even be a trace in the original algebra, but we can nonetheless derive a trace inequality. We also derive, via some more work, another generalized Golden-Thompson. Again, it's sort of coming from a matrix inequality that was in that original paper. But in this case, again, we're able to rewrite the inequality entirely in terms of Kosaki and Hagger Up norms. Now, what's interesting about the left-hand side of this inequality is that we're actually sort of mixing something in the L1 space that's here weighted by P with a sum of bounded operators in the algebra. And on the right-hand side, this x0 is going to correspond with the weighting density rho for the Kosaki norm. So from this, from these ideas, we can get a p-Fidelity generalization of recovery, where the p-Fidelity is now this parameterized fidelity that includes the original. This will actually subsume the recovery result from Junge and co-authors in 2018. This holds in general von Neumann algebras, and it also gives some of what we might think of as nonlinear recoveries when p is not equal to 1, which relate different powers of these densities. We do also get a recovery result in the form of the measured entropy, and this in principle would follow from the generalized Golden-Thompson inequality, but in practice it's actually easier to use the Golden-Thompson inequality in type 2-1 and then use the Hagger Up reduction with the relative entropy. So instead of just trying to go directly, the continuity is easy to do everything as possible in type 1, type 2-1, and then use this sort of approximating sequence. And finally, we get another saturation condition. When the relative entropy is unchanged under the action of a channel, there exists this L1 isometry that sort of serves, it implements the channel, and of course it has an inverse. And this is sort of an alternative to the Petz map condition. This is sort of a more a mathematically motivated condition where this isometry will be usable on a wider domain given by this subalgebra that contains one of the input states. So this is where I'll conclude. I think that I'm already basically out of time. So these three ideas I showed, the multivariate trace inequalities, general von Neumann algebra recovery inequalities, and the saturation condition.
Okay, so I guess let's thank Nicholas for this very nice talk. I'll open the floor for questions, and this time I promise I'm in the right Slack channel. So in the meantime, maybe I'll ask a dumb question from a finite dimensional guy. So at some point when you were talking about the Haagerup LP space, I guess you were talking about this as a trace. It has a trace somehow in quotation marks. Like maybe you can discuss on why it's a quotation mark trace and not a real trace. Like I realize this is really basic stuff, but I'm curious.
Yeah, so this will act like a trace on densities in the Haagerup L1 space. This is not actually a trace on M. M doesn't have a semi-finite trace. And in fact, I think the thing with M is that you can try to construct a trace on it, but you'll find that it's just like equal to infinity all over the place.
So what's the missing thing for it to be a real trace?
So what makes this Haagerup trace different than the like having
what makes it not a trace?
Well, I mean, this is defined on a different space. It's not on the von Neumann algebra itself.
I see. Yeah, thanks. So now we have a question in the Slack channel from Lee Gao, who's asking how the p-Fidelity correction term in the recovery depends on p.
So we haven't actually explicitly calculated these too much. I mean, I think this is sort of, there's an analogy to be made where if you take like these p quantities, these are more sensitive to, as you take p higher, what you would find is that these are more or less sensitive to like larger eigenvalues versus the, or larger singular values versus sort of the number of non-zero singular values. It's sort of, you can get a bit of intuition for this by looking at like how this would look with finite dimensional vectors.
Okay, thanks. Yeah, I don't think we have any more questions in the Slack channel. And in any case, I guess that we've reached the end of the session anyway. So first of all, I'd like to thank Nick again for this very nice talk and all the speakers of the session, in fact. I'll clap for the audience as a whole. And before I close the session, I'd like to remind everyone that if you'd like to hear more about any of the talks that we've had in this session, there's a roundtable going on basically right now. And in fact, there are 3 roundtables, one for each talk in this session that you should be able to access by, I think there should be a button below the stage, something like that. So yeah, I hope to see you there. And on that note, I'd like to conclude this session, and I guess we'll come back at 7 p.m. for the session 4s.